Let me see here. Actually, this wasn't from today, but it's a fundamental theorem of calculus.
Okay.
I got some problems on here.
Okay.
Just a second.
There's two parts to the fundamental theorem of calculus.
Um,
The one part is fairly obvious as to how you evaluate an integral once you've found its antiderivative.
mm-hmm. Yeah,
Go ahead.
I'm gonna have to probably send these to you.
Okay. Do you have my email?
Just remind me of it again.
Here, let me write it. I actually have a couple. This one gets to me the fastest. The others have to be forwarded. So if you're going to attach a file or anything, send it to this one. That's supposed to be Gmail.
All right. I just sent you number one.
All right, let's have a look. And then this one, can I download that? That looks like it's embedded. Here.
Oh, okay. You want me to attach it?
Attach it if you would, because when it's embedded, I can only see it. I can't blow it up.
Okay.
Enlarge it or anything.
Okay, there we go.
Okay. The graph of f is shown, and let a of x be the integral from -2 to x, and f of x the integral from 4 to x. And that's the two area functions for f. Evaluate the following area functions. All right, let me take a picture of this so I can draw on it. So that is the area from there to some x.
Okay.
Okay. And this is the area from there to some x.
Mm-hmm.
Let a be the integral of f of t, which is our function, And this is the integral of f and t. So, let these be two area functions for f. So, if we had, let me think about this for a second here. All right. So what that says is, what is the area from there to there? What's that area?
From -2 to -2. Be 0.
Okay. What is from 4 to 8? What's that area? Because they're talking about capital F of A, of 8. So what they're saying is this. That's got to be the integral from 4 to 8 of our function. So it's the area between the x-axis and the curve. Well, it's telling us that that area is 9. What is it, though? It's actually -9.
Because it's below.
Because it's below, exactly. Now, A of 4 is the area right there. In other words, it's from -2 to 4. So it's asking us what the area is. And they've given us the areas there. So what is C? What is this?
So that would just be the first two areas, right?
24, exactly.
24.
F of 4 is, again, our function from 4 to 4. That is always 0. Whenever you go from your lower limit of integration to your upper limit of integration and they're the same numbers, that area is always 0. Finally, A of 8 would be the area, the net area from there to there.
So from the -2 to the 8? So it'd be 24 minus 9, 15?
Correct. Now, yeah, just to be clear here, what that means is that function, so A of 8 is going to be the integral from -2 to 8 of f of t dt. And what that means is the area under the curve. That's what integrals mean.
Right.
Okay, what else you got?
Some of these questions, I already have them answered, and so, but not all of them I'm exactly clear on how I got to the answer.
Okay, you want to send me a picture of it, or is it stuff you can verbalize?
I'll send you a couple pictures here.
Okay.
Just a second. Okay.
The fundamental theorem of calculus, and really the two parts of it, like I said, one is very, very clear and easy to understand. The other one is a little bit strange, whereas I think I can remember it. Let's see. The one part of it that's not quite so obvious here, as soon as I get a chance to write, I will. Just a moment. And that is, if you take the derivative of the integral of a function that goes from some constant to a variable, that is always f of t. And this is what's unusual, is that you rarely take the derivative of an integral.
Mm-hmm.
But it basically cancels out. But
right.
The strange part here is that as long as it goes from a constant to x, then it's always actually f of x, not f of t. It's always f of x. No matter what the constant is. That constant can be minus 100 or it can be a million. As long as it goes from a constant to the variable, then your final answer is f of that variable, x.
Mm-hmm.
That is actually part one of the fundamental theorem of calculus. And the other part would be this. When it's going from limit a to b, then that is always going to be the antiderivative of the function evaluated at b minus the antiderivative of the function evaluated at a. And this is the part we're always using. This is how we find areas under the curve. Usually we know the function, so we can find the antiderivative of it. And then the way we find the area is we find the antiderivative of the function. That's what capital F means. It's the antiderivative of little f. We evaluate it at the upper limit, and then we evaluate it at the lower limit, subtract the two. That's how you get the area. Now, that last problem we just did was a little different in that they did not tell us what the function was. But they showed us the function, and they gave us the areas that we needed. So we were able to do it. All right, so you got another one, I think. I've got another email here. That's probably from you. Okay, which page do you want to look at first?
We can just do them in order.
Okay. Choose the correct graph. Okay, well, we're going to use the second part of the fundamental theorem of calculus. In other words, I'm going to find the antiderivative of that. I'm going to evaluate it at 3, and I'm going to subtract the evaluation at 1/3.
Okay.
Okay. Now, I didn't, let me, hold on a second. Let me get that eraser and erase what I've written there, because I wanted to do this in ink space. Now this is a relatively easy one to find the antiderivative of, because it's the difference of two functions. In other words, as long as I can differentiate, as long as I can integrate that, and as long as I can integrate that, then this is pretty easy to integrate. So what is it?
So it's x.
Best way to do these so you don't make a mistake is to first of all write it with a negative exponent. Now it's easy. In other words, now you add 1 to the exponent and divide by the new exponent.
So it's just negative. It's negative 1 over x, right?
Well, let's add 1 to the exponent, divide by the new exponent, so that these become positive, and you get
right.
just 1 over x. Exactly. A positive 1 over x. So that is this. That is the antiderivative of this function. And then to evaluate it, you're familiar with that sign?
Not exactly.
What that little right bracket kind of means is it means evaluate this function at 3. In other words, it means f of 3 minus f of 1/3. That's the fundamental theorem of calculus. You take the antiderivative, which is capital F, you evaluate it at the upper limit. Okay, so what is capital F of 3 equal to? We're plugging it into that. There's our capital F function.
Okay, so it's going to be 3 plus 1/3
minus.
So, and that's also going to be 3 1/3, right?
Yeah, and be very careful here that you use parentheses. Otherwise, it's really easy to get it screwed up. In other words, yeah, that's 1/3 plus 3. And I am subtracting that whole thing. That's why you got to use parentheses. If you don't use parentheses, you would not get the correct answer, which is 0. Now, so what that tells us, oh, there's the answer. Was that there all along, staring at us?
I think it was, yeah.
So our only goal is to make sure that when we find a graph where when I go from 1/3 to 3, I've got a net 0 area. Okay?
Okay.
Now, where is that? That looks awfully good. There's a problem. Well, is there a problem? Yeah, that one's not going from 1/3. That looks like it's going from 0. Whereas that does look like 1/3. That's not it. For one thing, we're looking for a net area of 0, and that certainly doesn't have a net area of 0. Whereas this looks like the part above the x-axis is about equal to the part below the x-axis. And furthermore, I guess I don't need a furthermore. In other words, I was able to choose it by process of elimination, really. But the question is, can I graph that? That would be x squared plus 1 all over x. That is going to have a slant asymptote. I don't see any of those that have a slant asymptote. No, it's graphing that.
Oh, okay.
Not the antiderivative. We're not graphing the antiderivative, we're evaluating the antiderivative. So if I graph that, it actually becomes x squared minus 1 over x squared. And that does have a horizontal asymptote at 1. So D doesn't work. That has a horizontal asymptote at 2. This one has the right horizontal asymptote. This one does not, but so does this one. They both have a horizontal asymptote at 1. But clearly this has a positive area, not a net 0 area. I actually think these are the same two graphs. That pink graph is the same as that pink graph. It's just this starts from 1/3 and this starts from 1.
Right, okay.
Okay. So it's very clearly B. All right, let's take a look at the next one. Another one that we can do the math on. I guess I'm a little confused here. Why are they giving you the answer, or are they?
This is from a homework that I've already done, but
so you
sometimes
you didn't have that answer to begin with, right?
Right, yeah, but sometimes I do the homework while the lesson is going on, so I kind of use the lesson to do the homework, and then after I kind of forget how I did it.
Okay, so we need to do this from scratch? Just to make sure that that 17/3 is correct?
Right.
Okay, so what's the antiderivative? Always write these, I think it's always worth writing it using no radical signs. So there's our function. Now it's pretty easy to integrate or find the antiderivatives of that. What's the integral of that?
So that's just going to be x squared minus x to the...
I think it's worth just filling in stuff here. I'm going to add 1 to the exponent, divide by the new exponent. In other words, get to that step and you know you're not going to make any mistakes. Okay, now I can simplify that to x squared minus 4x to the 3/2 over 3. Believe I did my math right. And I'm going to evaluate it from my lower limit to my upper limit. So that is 16. Always do the upper limit first. Let's see, 4 to the 3/2 is 8. Times 4 is 32.
Okay.
So we have 48/3 minus 32/3. So I got 16/3. Hold on. That's just the upper part.
Oh, okay.
Not just that part. Now I have to subtract off the function evaluated at 1, which is 1 minus 4/3 which is minus a third, which is plus a third, which is 17/3. So
Okay.
math was fine. Now, how do we pick? Are there only 3 answer choices here?
Yes.
Okay, so first of all, that one's not right because it goes from 0 to 4, right?
Mm-hmm.
In other words, that one starts there. So this one's going from 1 to 4, so that could certainly be the correct one. That's not right. That goes from 0 to 1.
Yeah, I guess I didn't make that one very hard.
Yeah. Now, does this equal 17/3? Well, we can approximate it. 17/3 is almost 6. Well, there's 1 square, 2 squares, 3 squares, 4 squares, almost 5 squares. Looks like 17/3 to me.
Okay.
And really, we don't even need to do that part of it. Is all we need to do is have our eyes look left and right to eliminate A and C.
Mm-hmm.
B has to be it. It's the only one that goes from 1 to 4. And it's always the area under the curve between the function's curve, the x-axis, and those two numbers, 1 to 4.
Okay. That one's probably easier than I thought it was.
Yeah, I mean, it's not terribly trivial coming up with the 17/3, but
Mm-hmm.
I'm not sure what the point of these questions are after that. They
Yeah.
all seem relatively easy once you've come up with the area, I guess. I'm not even sure that's necessary, but I assume that's part of the problem. So you had to come up with that, right?
Yes.
Okay. Just curious as to whether we could figure this one out without coming up with this. We could have the last one. We're going from -2 to 5. That one's out. That one's out.
I think both A and C work for that, though.
A and C do work. One's positive, one's negative. So I guess we're going to have to verify your number. And that's the only difference between them, is one's positive and one's negative. Now, I actually don't need to do anything more. This is the function. That's a parabola that opens up. Has to be that one.
Mm-hmm.
In terms of coming up with the number, since that's part of the problem, let's do it. So it's x cubed over 3 minus 3x squared over 2 minus 10x, evaluating from -2 to 5. So let me do it down here. I really think that it's worth just plugging everything in and not doing any math at all the first go around. I'll show you what I mean. I'm not doing anything in my head. It's too easy to make a mistake.
Mm-hmm.
Okay, now I'm going to subtract. Always use brackets because you're always subtracting. So whatever goes in these brackets has to be subtracted from the first part. Okay, now I'm going to put in -2, cube it. I'm assuming that this is the way you did it. Now I can simplify it. So let's see, that's 125 thirds minus 75 halves minus 50 minus, let's keep the brackets there for a moment, that's minus 8 thirds. That's still minus 12 halves, which is a 6, and it is still a minus 6 inside the bracket, because that minus 2 turns into a 4. Okay, and then inside the bracket, it's plus 20. And now we want to remove the bracket. So that becomes a plus, that's a plus, that's a plus, that's a minus. So what do we got here? We've got 125 thirds minus 75 halves minus 50 minus 20, that's minus 70, plus 8 thirds plus 6. And we're going to use a common denominator of 6. So that's 250 minus 225. These are all over 6. Minus 420 over 6 plus 16 over 6 plus 36 over 6. Okay. I don't know, at some point this just becomes an exercise in arithmetic, but it's always nice when you do it and it comes out right. So let's see. We got 25 sixths plus 52, that's 25 plus 52 minus 420, so that is 77, and I get 343 negative sixths. And my answer agrees with yours.
All right.
Have they taught you how to do these with a calculator?
Yeah, but I'm not sure if we'll be able to use them on the quiz.
No, certainly this one they would not want you to use the calculator on. I just was curious as to whether you knew how to do numerical integral. What kind of calculator do you use, Chris?
TI-84.
Okay.
Yeah, they actually didn't tell us.
Numerical integration. In other words, you can put this in, and it will give you back minus 343 sixths, or at least a decimal. Not sure it'll give it to you as a fraction, but
yeah, they didn't tell us how to do that in math. They told us in physics. So maybe my math teacher's trying to keep that a secret.
Oh, in terms of doing the numerical integration?
On the calculator, yeah.
Oh, they haven't taught you that in math yet.
Not in math, but in physics.
Oh, well, she probably is trying to keep it a secret. She doesn't want you to know how to do it, because that will, change everything.
Yeah.
As you can see, there was quite a bit of arithmetic on that. A lot.
Oh, yeah.
And it would have been extremely easy to make a mistake. So the one advantage of being able to do it in your calculator is you get to check your work. In other words, when you come up with this answer, now you stick it in your calculator and it agrees and you know you've done it right. Whereas if you don't have that calculator method to do it, it might You might spend a little more time doing all that arithmetic to make sure you get it right. But again, we didn't need it to graph it properly.
Right.
Was there a third one? Or was this the third one?
I think that might have been the third one.
Yeah. It was that one right there.
So I'd kind of like to do just a few more of the ones we were doing yesterday.
Okay.
We get back to that homework.
I'm just going to use this as my drawing board here.
Okay. I don't think I'll have to send these to you.
No, if you can verbalize them, I'll just do it on this piece of paper here and I can erase.
Okay.
There's an advantage of using this drawing board as opposed to my other one that doesn't allow me to erase.
Mm-hmm.
And that has to do with the fact that it's not synced up with OneDrive. I had to uninstall OneDrive on my computer.
Okay.
Screwing things up for me, big time. So yeah, if you want to just write it here, or give it to
yeah, sure. So this one is a little simpler than the ones we did yesterday.
Okay.
But I kind of need a refresher on these. It's dx over 2x plus 1.
Okay. Yeah, I was sitting here trying to think of, do we really need U substitution here? I suppose we do, because it's not the natural log of 2x plus 1. Notice why it isn't. In other words, if I didn't realize I had to do the chain rule here, I might come up with this as an answer, right?
Right.
But if I take
why is it
the
not that?
derivative of that, I get 1 over 2x plus 1, but then I got to apply the chain rule, multiply it by the derivative of the inside, which is that. So that is not the answer. So let's use U substitution. And notice there's two types of U substitution. I don't know if they've taught it to you this way or not.
You told me a little about that yesterday.
One of them is pattern recognition. Okay? Pattern recognition is where you have f of g of x, a composite function, followed by the derivative of the inside, or multiplied by the derivative of the inside. So when you see that, that is perfect for U substitution. And the other kind is merely called change of variable. And that's where you don't have anything that looks like that, but you have something that looks like that. In other words, what we're looking at is certainly not the pattern recognition. We're not looking at the derivative of the inside anywhere. So we'll use the, obviously I'm going to let U equal to 2x plus 1. In other words, I'm not going to use that. And now du dx is equal to what?
2.
Okay, which makes du equal to dx, which makes, this time I'm going to do it the long way, just because it's a little clearer. So now if I want to write this as an integral in u, well, what is dx? Dx is du over 2, and u is that, so my bottom is u. And now I can integrate that. And I can take the 2 out of the bottom, make it look like this. In other words, you can take constants out, just can't take variables out.
Right.
And that now becomes 1/2 natural log of u, which is 2x plus 1. Now, if I differentiate that, I will get back to my original function. Notice that I'll have 1 over 2x plus 1 times 2 divided by 2.
Okay.
And I'm trying to think. Yeah, there's one other way I could do this. It might be worth looking at, where I don't really use u substitution at all. I'll show you what it is. Here, let me erase everything and rewrite it. Integral of du over 2x plus 1. Now, if that denominator says x plus anything, then my answer is the natural log of it. So, how can I do this? What if I divide the inside by 2 and multiply the outside by 2? As such. When I divide the inside by 2, I get this. I get that. Excuse me. Now, do you see where that is the same as this?
I think so.
Well, bring that 1/2 back inside the integral. Then that 2 goes on the bottom, so you end up with 2x plus 1.
Okay.
The advantage of doing this is that now that's natural log of x plus 1/2. And this 1/2 comes along for the ride.
So the only time you can't do the natural log just right off the bat is when there's a coefficient in front of the x?
Did I get this when I did u substitution? I don't think I did I? I think I got 1/2 natural log of x plus 1. Let me re-examine the u substitution here. I've made an error here, I think.
Okay.
Let's just re-examine. In other words, yeah, just to verify that that is the correct answer here. So if I let u equal 2x plus 1, it certainly makes du dx equal 2. Furthermore, it makes x equal to u minus 1 divided by 2. So now, if I merely substitute everything for du, I'm going to write the integral of 2 dx all over, excuse me, I'm going to write for du, I'm going to write 2 dx. That's, well, first of all, that was a dx to begin with. So let me back up. It never helps when you make mistakes. So
Okay.
dx is du over 2. So there's my du over 2 and times u. I do get the same answer, I believe. I'm going to take the half out, and so it's going to be 1/2 the natural log of u. And that is 1/2 the natural log of u, which is 2x plus 1. It is a different answer. And this I know is correct because I know if I take the derivative of that, it's 1 over 2x plus 1 times 2 divided by 2. So I know this is correct. I must have done something wrong in my arithmetic when I tried to do it without u substitution to get this answer over here. Somehow I have an x plus 1/2 over there instead of a 2x plus 1. So I guess that the moral of the story is use u substitution rather than trying to do it the other way where I'm trying to factor out a 1/2.
Okay.
Yeah.
Yeah, I think on most of them that are harder, I'll have to use u substitution anyway.
Well, they want you to anyway. I just thought that I saw a different way to do it, but let's try another one.
All right. How about x to the 3/2 plus 6, all of that to the 8th times the square root of x.
Okay. Notice we can't really do this the normal way. I mean, I could expand it out. That would be extremely laborious. But notice the pattern recognition that we're looking for. Remember what we're looking for? We're looking for a composite function multiplied by the derivative of the inside. Well, here's my composite function, and the derivative of the inside is going to be x to the 1/2. Now, there's some other numbers that go along with that, but those don't matter. It's the degree of the x that fits. In other words, that right there is the derivative of the inside of my composite function. So I know that this is perfect for u substitution. I notice it right off the get-go. At some point in calculus, you're going to be given problems, and you're going to have 5 or 6 methods of integrating it, and you're going to have to select which one you want. Okay? And so you would say that this is perfect for u substitution, as opposed to one of the other more complicated methods, merely because I am multiplying by the derivative of the inside. So work me through this. What's u going to be?
It's just, sorry about that. It's just going to be the inside, right?
Correct. The inside of this composite function. So what is that?
X to the 3/2 plus 6.
Now the next step is to always differentiate this thing. What's that?
So that would be 3x or 3/2 x.
I always just take that exponent and write it out in front. If there's another number already out there, then I multiply it by that number. Just so that I don't, in other words, I'm following a pattern that never changes. I always start with the exponent. When I'm done, I subtract 1 from the exponent. Okay. Now notice that I've got my x to the 1/2. I still have this 3/2 here, but I can take care of that, and I'll show you how. So the next thing is to get the dx on the other side. The next thing is, this time, let's just get the 3/2 on the other side. Well, I got to multiply both sides by 2/3 to get rid of that 3/2. Okay. Now, instead of solving this thing for dx like we've been doing, notice we're looking at exactly what we see right there. X to the 1/2 times dx. So I'm taking this part right there and I'm going to substitute 2/3 du for it. You with me?
Okay. Mm-hmm.
It's a little easier to do it this way. In other words, once you get this right side of the equation to match something that you're looking right at, it's even in the right order. It wouldn't have to be in the right order. So now I can rewrite this whole thing completely as an integral of u. What would it be?
So the first part would just be u.
To the 8th.
U to the 8th, right?
Yep, don't forget that 8.
Mm-hmm.
That's
Time.
the only reason we're using u substitution here is because of that 8. Otherwise, we could multiply this polynomial together and just do it as a polynomial.
Mm-hmm. So that's going to be times 2/3 du.
I'm going to put the 2/3 there. I'm going to put the du there. And now I'm off and running. Now it's a piece of cake. Again, how do I do this? I always start with that and just add 1. I leave the 2/3 there. I don't touch that. I put the u, I add 1 and divide by the new exponent. So there's my answer. Well, not quite. 2/27, and it's u to the 9th, but u is this. So it's x to the 3/2 plus 6 to the 9th plus c. That is my integral of those functions. And I don't know that there's another way to do it other than take that to the 8th power, multiply the whole thing by x to the 1/2, and then just deal with a 9-term polynomial.
Mm-hmm.
And I would get the same answer, but it would be a lot harder.
Right.
Got time for one more if you want.
All right. Let's see here.
And there's really only 2 types of these. There's the pattern recognition, and then there's the change of variable.
Mm-hmm.
And if you know you're supposed to use u substitution and you don't see any pattern recognition, you know it's got to be the other one. It's got to be the change of variable method.
Right. Okay, so here's one. So the quantity of sine to the 4th of x minus 5 sine squared of x plus sine x, and that's all times cosine of x.
Okay, what do you recognize here?
Kind of looks like the one where it's the function and then the derivative.
Yeah, the cosine of x is the derivative, except, well, first of all, yeah, here's what we want to do. We want to distribute this cosine of x. Okay, and turn this into 3 problems. Here's one of them. Here's the second one. And the third one. Now, we're going to do each one of them separately. That sine to the 4th of x is a composite function. And the derivative, what's the inside? If you were going to differentiate that, and I said, what's the inside of sine to the 4th of x? It's sine x. Well, what's the derivative of sine x? Cosine x. So we definitely have the f of g of x, that's this part here, times the g prime of x. That's that part there. And so what we're going to let u be is sine x. And after a while, you kind of get to the fact, you get used to the fact that this derivative is going to just disappear, and this thing's going to end up being sine to the 5th of x over 5. That's going to be the answer to this part.
Mm-hmm.
This part is going to be sine cubed of x over 3, or 5 sine cubed of x over 3. And this part is going to be sine squared of x over 2. And there's your answer. Now, it takes a while after doing a bunch of these before you can jump directly from that to that.
Mm-hmm.
Notice I didn't go through all of the u is sine of x, which makes du equal cosine of x dx. And so wherever I see that, I'm going to stick a du. And I've got it right there. So that becomes du. So it's u to the 4th du, which is u to the 5th over 5, which is sine to the 5th of x over 5. So when it's a perfect derivative, like this case, then you can just kind of use the power rule. Notice my answer is basically the power rule here.
Mm-hmm.
Starting with the sine to the 4th, adding 1, dividing by the exponent. It only ends up that way because it's being multiplied by the derivative of the inside.
Right.
But when you have it perfect like this, you don't need to actually go through it. I've seen it taught by calculus teachers where they don't call this u substitution. They call this the power rule. Serious. They do. I didn't like it the first time I heard it. I'm still not sure I like it. Because you can't really use the power rule. In other words, you're going to find people that if you say, what's the integral of that? They're going to say sine to the 5th over 5. And that's not the case. It's only the sine to the 5th over 5 if there's a cosine x multiplying.
Mm-hmm.
You got to have that derivative of the inside being a multiplier before you can say that you're using the power rule.
Right.
Because, yeah, a lot of people would make this mistake. If you ask them, what is the integral of sine squared of x, they would say sine cubed x over 3, and that is not the answer. That's actually pretty hard to do.
Yeah.
It's not. It looks like it would be trivial, but it isn't. It's trivial if there's a cosine x next to it, but if there isn't, I'm not even sure how I would go about doing that. I guess I'd have to play around with it and think about the 6 or 7 methods that you have for integrating.
Mm-hmm.
But you should be pretty set to do U substitution.
All right. I feel pretty good about it.
Yeah, I do. I feel pretty good about your knowledge too. I wish you were taking your test tomorrow.
Yeah.
And having to wait next week for it. So.
Yeah, but I'll try all the homeworks again this over the weekend, so I
All right.
can get it down.
Chris, if you need any more help, let me know.
All right. Thank you.
You're welcome. Bye-bye.
Bye.